All right, so today we're talking about the mean value theorem, and my expectation is that you're reading through the notes before going over the examples that we have here on the video. I'm only discussing the examples, so it's your responsibility to make sure you go through and read the inside parts of the notes to understand what the mean value theorem is and what it tells us. So first basic problem of the mean value theorem is exactly this. Mean value theorem says that somewhere on an interval, if you're continuous on a closed interval and differentiable on, oh, you gotta be kidding me. So the mean value theorem says that if you're continuous on a closed interval and differentiable on an open interval, then you are guaranteed that somewhere along there, there's going to be at least one x value guaranteed where the instantaneous rate of change matches the average rate of change. So let's go through and do that. All we have to do is find the average rate of change, compare that to the instantaneous rate of change. So our instantaneous is going to come from the derivative. So our derivative is going to be f prime of x equals 3x squared minus 2x minus 2. And then the average rate of change is going to come from f of 1 minus f of negative 1 all over 1 minus negative 1. We end up getting a negative 1 for the answer here. So what I'm going to do is take that and set it equal to my instantaneous rate of change, which is given by the derivative. Somewhere along that interval, the instantaneous is going to equal negative 1. So we go ahead and set that up. 3x squared minus 2x minus 2 equals negative 1. So then from there, I've got a quadratic to solve. So we'll go ahead and go 3x squared minus 2x minus 1. So we've got this factored out. This is where we're at right now. So from there, we're going to find both of those solutions. It looks like I get x equals negative 1/3 and x equals 1. Now, I have to be very careful on which one I choose. Turns out 1 is on our interval that's given to us, but it's not guaranteed by the mean value theorem because, well, we need to be differentiable on the open interval. So we're not including 1, even though it's continuous there as well. So this endpoint is not guaranteed by MVT. So the answer we have is right here. X equals negative 1/3. That's the moment at which the average rate of change equals the instantaneous rate of change. Looks like we've got a rational equation, a rational function, x plus 5 or x minus 1, on specifically the interval negative 3 to 5. What I notice about this function is we're undefined when x equals negative 1, I'm sorry, x equals 1, and that's a big problem with the mean value theorem. I need to be continuous on the interval, and x equals 1 is inside the interval. So therefore, MVT does not apply because f of x is not continuous. Now, it's not continuous specifically on the interval given to us. If we had a different interval that did not contain this discontinuity, we could apply the MVT, but that isn't the case for this problem. First thing we're going to look at is when f of x is increasing. So we're going to make this statement. When f of x is increasing, then we know f prime of x is positive. When f of x is decreasing, we know that f prime is negative. And then when f of x is constant, we can say f prime of x equals 0. So the first thing we're going to do is figure out where our critical values are, because we know that the sign of the derivative, when it changes sign, we're changing direction on the original function. So let's find our critical values first. We're going to set the derivative equal to 0. First thing we're going to point out is that neither one of these functions are ever undefined, so we never have to worry about figuring out, well, where's the derivative undefined, or do we have any discontinuities in f of x that we should be aware of? So first thing we'll do is start factoring this out. This is going to boil down to 2x squared minus 5x minus 3. And when we factor that out, I think we can think through that one. That becomes 2x minus or plus 1, and then x minus 3. So from there, we get two solutions to the quadratic. We get x equals -1/2 and x equals 3. Now these are both of our critical values. I'm just going to put CV there for critical values, what we've been talking about a lot this week. And we're going to take those two critical values and make a sign chart to help us determine intervals of increasing and decreasing. So all I do is put together a sign chart, and the critical values are the only things I really need to worry about for this one because I'm never undefined. I have -1/2 and +3. So what I'm going to do is do two things. I'm going to write down above, what is f prime doing? That should be f prime there. And then what is f doing? So when I look at f prime, if I use a test value, say a test value of 0, if I plug in 0 into the derivative, I get a negative value for the derivative. So I'm going to plug that in. And when I plug in any value less than 1/2, I get a positive value for the derivative, and a positive value for the derivative when I plug in any number greater than 3. I know I get 0 when I plug -1/2 and 3 into the derivative. But now I determine, what does the derivative tell me about what the function is doing? Well, since the derivative is positive, that means my function is increasing on that interval. My derivative is negative, I know I'm decreasing on that interval, and I'm increasing again. So what I'm doing is figuring out where I'm increasing and where I'm decreasing. So let's go with increasing and decreasing first. So I know I'm increasing over the intervals -∞ to -1/2, and then also 3 to infinity, because f prime of x is greater than 0. That's the justification you need every time. I can also say I'm decreasing over -1/2 to 3 because f prime of x is less than 0. It's negative. And this is all the justification I need for increasing and decreasing. All right, next thing I'm going to do is take a look at where my local extrema are and justify that. This is the first time we've done that. What we did in the extreme value theorem lesson is determine where we have absolute extrema and absolute minima. Now we're looking at local extrema and local minima. Because it's a cubic function, I don't have any absolute extrema or minima. I only have locals. So we're going to figure out what's happening here. So if I look at the change in sign for the derivative, I see that I'm increasing and then decreasing, and that implies that I have a maximum at -1/2. So here's how we justify. We're going to say that we have a relative maximum at x equals -1/2 because f prime of x changes sign from positive to negative. That is the justification we need for local maxima and minima, local extrema. You can also say we have relative minimum because we're changing direction. The derivative is changing sign, and that implies the function is changing direction. So we'll say we have a relative minimum at x equals 3 because f prime of x changes sign from negative to positive, and that is the justification you need to back up your answer about how you know that that's a relative minimum or not.